Hi, good morning to all. Today we are going to see thin film physics. Within this, at first we see what is meant by thin film and we see the different deposition technique process. Okay. The first thin film was observed by scientist group from sputtering of cathodes with a high energy positive ion. Later it was developed as a new field. Nowadays it has an extensive applications in so many industries like electronic industries, photonic industries, space science, aircraft, defense, etc. Okay. First, we see what is meant by thin film. A thin film is a microscopically thin layer of material that is deposited onto a metal, ceramic, semiconductor, or plastic base. The thin film may be a dielectric or conducting nature. They have on the basis of the thickness, it has in three classifications. One is the ultra thin. It has a thickness of 50 to 100 Armstrong. And 100 Armstrong to 1000 Armstrong film is called as a typical thin film. And greater than 1000 Armstrong film is considered as a thick film. Okay. The thin film has three important properties like physical and electrical and optical properties. And these properties are fully depends upon some parameters like rate of deposition, substrate temperature, environmental conditions, residual gas pressure in the system, and the purity of the materials, etc. Okay. The thin film deposition techniques. Okay. Generally, the thin film deposition has a four sequential step. The first step is the source material, that is the target, is converted into the solid or liquid or condensed phase. The second step is from a condensed phase, it is converted into the vapor form, atomic layer, or ionic. And third step is it is transported into a substrate by applying the pressure, voltage, and magnetic field. Okay. The fourth step is it is then made to condense onto the substrate to coat a thin film. Depending on low the vapor form is created for condensation process, the thin film deposition method can be classified as two types. One is the physical method, another one is the chemical method. In chemical methods, we have the familiar techniques like the spray paralysis, sol gel, chemical water deposition up to electro deposition process. Similarly, the physical methods also have the two wide branches. Only the one is the evaporation, another one is the sputtering. Further, the evaporation have the five important techniques like vacuum evaporation, electron beam evaporation, laser beam evaporation, arc beam evaporation, and ion beam evaporation. Similarly, the sputtering also having the three important techniques. One is the magneton sputtering, reactive sputtering, and beam sputtering. Now we see the thermal evaporation techniques in physical method. Here I show the schematical experimental setup for the thermal evaporation method. The thermal evaporation method is one of the important method in physical process because of the simplicity, and then the rate of deposition is the notable strength of this technique. In the thermal evaporation experimental setup has the three important parts. One is the bell jar, another one is the filament boat filled with the evaporant. Third one is the substrate, the substrate holder. Okay. Here, before starting the coating process, first we have to create the high vacuum inside the bell jar using the rotatory pump. Okay. The target material is located inside the evaporation source, that is called as a boat, coil, and basket, which is heated by the passage of electric current. After the passing of the electric current, due to the resistive heating, the temperature is developed inside the evaporant. Okay, that's why it's called as the resistive evaporation method. So the thermal evaporation method has another name like a resistive evaporation method. After the evaporation, the molecules of the target material move to the substrate and form a thin film on the surface of the substrate. So using the thermal evaporation method, we can deposit the aluminum material, silver material, nickel, and chromium and magnesium, etc. Okay. In thermal evaporation method, we have to concentrate the two type of collisions inside the chamber. The first collision is the interactions between the evaporant and the molecular, the gas is filled within the bell jar. Another one is the interaction between the evaporant and the condensed moisturized content like oxygen molecule. Okay. So the first interactions lead to the imperfection and or impurity of the film surface. To prevent this, the thermal evaporative deposition process must be performed in a high vacuum environment. Okay, at a pressure of, that is the pressure of 10 to the power of -5 torr. These pressures restrict the molecular mean free path. That means the average distance traveled by the molecule in the vacuum chamber before colloiding with the another molecule is 1 meter. Okay, so the 10 to the power of minus 5 tor is restricts the molecular interactions between the evaporant and the gas filled within the well jar. As a result, the molecules of the vaporized material can be reached the substrate in a straight line without colliding with another molecules. The another interaction is the background gases. That is, the background gases create the moisturizing content inside the well jar. So that is the oxygen molecule. There is the oxygen molecules interact with the evaporant. It leads to the imperfection or impurity of the thin film. So by reducing this interaction, we have to reduce the pressure from the 10 to the power of minus 5 tor to 10 to the power of 6 tor. The purity of the deposited thin film and the performance of the devices will increase significantly. Okay, the thermal evaporation method has so many applications, but I listed three only here. The first one is we can create the metal bonding layers in devices such as YLEDs, solar cells, and the thin film transistor, and we can create the metal backing plates also. And using thermal evaporation method, we can produce the aluminum sheet. Here, the aluminum material is coated on the polymer. As a result, we have the cheapest alumina sheets. In these alumina sheets are used to packaging of food or decorating the food or heat and sound insulation. Okay, so next one method is the flash evaporation method. This is similar to the thermal evaporation method. Here I show the schematic experimental setup of this flash evaporation. In the setup has the three important parts. One is the AC vibrator, another one is feed tube and molecular board. The main difference between the flash and the thermal evaporation method is here the molecular evaporant is put into the molecular board in a powder form. Okay, the molecular board must be made with the tungsten or molybdenum or tantalum. Okay? Generally, the flash evaporation is a constant method for the preparation of the stoichiometric film of metals whose constituent elements have widely different even vapor pressures. In such a technique, the board temperature is maintained high enough to ensure complete instantaneous evaporation of small grains of the material fed to the preheated board. That is the important condition. That is the preheated board. The evaporated material condenses on a substrate to provide a desired film. Next method is the electron beam method. Here the electrons are produced with the help of the tungsten filament, and these electrons are converted into electron beam with the help of the magnet, and these electron beams are focused towards the target material. Okay, which is shown in the schematical experimental setup here. The electron beam method is a process in which a source material is bombarded with an electron beam generated by a tungsten filament under a high vacuum. This is the important condition. We should be perform under a high vacuum condition. Okay, this deposition method utilizes a stream of electrons accelerated through 5 to 10 kilo electron volt fields, which are focused on a target material to be evaporated. The electron beam forces the atom from a target to evaporate and form a gaseous phase. These atoms form a solid layer, thereby coating the substrate with a layer of the anode material. Okay, the impinging of electrons generate the heat required to evaporate the material to be coated. The purity of thin film coating is high using this method, since this deposition is carried out in high vacuum. Also, the rate of deposition can be regulated to be as low as 1 nanometer per minute to as low as few micrometer to per minute. Okay, this is the important advantages of this electron beam method. The electron beam method has so many advantages, but I listed out only the two important ones. Within this, the first one is the material utilization efficiency is high as compared to other deposition methods. This process offers structural and morphological controls of film. Due to very high deposition rate, electron beam evaporation method has a potential applications in aerospace industries, hard coatings for cutting and tool industries, and semiconductor industries. The electron beam method also has some drawbacks. One of the important drawbacks is the filament degradation in the electron gun results in non-uniform evaporation rate, and it cannot be used to coat the inner surface of the complex geometry. The next famous process is the sputtering process. Generally, the sputtering process is considered to be a most versatile thin film deposition techniques. Okay, it is a process whereby atoms are ejected from a solid source material due to bombardment by energetic ions, usually by means of plasma, which generates charged particles that are accelerated towards the surface, which is shown in here as a animated form. Okay, it produces coatings of device quality, higher purity, much controlled ethics with greater aggregations and great morphological of the thin films. This method basically involves the formation of ionized plasma of organ in the space between the two electrodes, that is the cathode and anode. When the voltage is applied between this cathode and anode, usually the cathode is the target material, and the substrate holder is acts as a anode material. The target material is bombarded with heavily by ions, ejecting atoms from the surface of the cathode through the momentum transfer. These particles diffuse away from the cathode through the plasma towards the anode, forming a layer of thin film on the substrate. The pressure inside the sputtering chamber during the process has profound influence on the uniformity, quality, and stress of the resultant film. In sputtering process, we have two important sputtering. One, it is this first one is the DC sputtering. Here, the DC sputtering experimental setup is shown. Generally, the DC sputtering utilizes a DC gaseous discharge. Ions strike the target, that is the cathode of the discharge, which is the deposition source. The substrate and the vacuum chamber walls may be the cathode. The power supply is simply a high voltage DC source. When the source of the ions is provided by the glow discharge created by an applied electric field between the electrodes in a gas at a lower pressure. So the gas breaks down to the conduct the electricity. This ionized gas or plasma is accelerated by a large electric field. When these ions impact the target, that is the atoms or molecules, are ejected from the surface into the plasma, where they are carried away and deposited on the substrate. This simplest and least evaporate method of sputtering is a DC sputtering, in which a DC power supply is used. In the system generally restricted for conducting material, because of a direct voltage is applied between the cathode and the anode. So the sputter gas used to typically inert gas like argon, in order to avoid any possible chemical reactions between the sputter atoms and the sputtering gas. Okay, during sputtering deposition, there is a chance to produce the forming of ox due to the accumulation of the oxides on erosion. Erosion groove edges where the rate of sputtering is low. Okay, the sputtering is the yielding of sputtering is increases with the help of the three important parameters. That is, we can increase the energy and the mass of the bombarding ions, and also with the decreasing of the angle of incidence of the target. Okay, and then the sputtering yield also decreases with the large increase of ions energy because of the due to the large ions energy, the deeper penetrations of ions are neutral inside the crystal lattice. Okay, the next sputtering process is the reactive sputtering. Here, the reactive sputtering is a process where a target of one chemical composition, that is silicon, is sputtered in the presence of gas mixture, that is the argon plus O2, that will react with the target material to form a coating of a different chemical compositions like silicon oxide. The most often used reactive gases are listed here. At first, oxygen are used to deposit the oxide film, and the nitrogen gas are used to deposition of the nitride films, and carbon dioxide is used to deposition of oxide coatings, and the acetylines are used to deposition of the carbide nitride films, and the methane it has a similar application as for C2H2. Here I show the racetrack diagram of the reactive sputtering. Generally, once a reactive gas is introduced into the chamber, it reacts with the walls of the chamber and the sputtering target also. Due to the sputtering process, an intensive erosion in the magnetron racetrack delays the compound formation. That is the new compound formation. Here I mentioned one word, fully poisoned. Fully poisoned means a new compound formed. Okay, in this racetrack diagram, as the two positions, one is the initial stage that is called the metal stage, and the second stage is the fully poisoned stage. In between the metal and the fully poisoned stage is called as a transition stage. Um, Using this transition stage, we can restrict the thickness of the film and the rate of depositions also. Okay, the starting stage is a metal sputtering mode, that is a clean metallic target racetrack, and again the last stage is the fully poisoned stage. Okay, the important the advantages of this operation is the transition region is a very flexibility region. In this region, we can fine tuning the coating of the chemical composition and the ability to optimize and improve the film qualities also. Next method is the radio frequency sputtering. It's simply called as the R.F.sputtering. The schematical experimental setup of the R.F.sputtering is shown in here. Here the R.F.sputtering experimental setup has three important parts like a substrate, another one is the target, third one is the shutter. Here this technique was reliable to deposit both conducting as well as the dielectric insulating samples. Using this technique, we can grow the high quality films in large area. In radio frequency system, a high frequency generator was connected in between the in electrodes. The high voltage RF sputtering source ionized the sputtering gas and to produce the plasma. A transverse magnetic field and the electric field is located under the target, which is directs the organ atom towards the sputtering target. Hence, the multiple collisions takes place. Finally, atoms of the target material are released into the plasma. Thus, atoms condense upon the surface, thus forming a new thin film. The permanent magnets are used to connect the general. Here, the permanent magnet is connected in the sputtering gun to enhance the deposition rate by trapping of the electrons. This magnet creates the line that is called the magnetic flux, which is perpendicular to the electric field or parallel to the target. Due to the secondary emission of electrons occurs and the number of collisions are increased near the target. Here I show the RF model discharge. Here in RF spectrometer there are four possible RF model are available, four possible models, which is shown in here. The first model model is at first, before starting the process, at first to place the insulator onto the cathode of DC discharge. Due to this, no current flow through the insulator, so no net current flow here. So the RF voltage is applied through an external capacitor. The input waveform is VRF frequency. Our radio frequency voltage always equal to the radio frequency of the sine omega t waveform. So we assure the amplitude of the radio frequency voltage is of the order of 500 voltage, which is shown in point A, and the point B shows the current that would flow to the target. The net current averaged over the period is not equal to 0. Okay, the point C shows the self bias of the blocking capacitor that develops because of negative charge accumulates RHS of the DC voltage to the RF voltage, the radio frequency voltage, which is amplitude is which is the amplitude of the applied voltage. Okay, and D shows the current flowing to the target with the self bias. The area under the curve D must be 0 for one complete period in a steady state. Here all the parameters are chosen to have a charging time of the blocking capacitor during the electron bombardment on the target not much greater than of the one radio frequency period. Okay, using these four RF models, we can quote the high quality desired thin films from the substrate. Okay. Today we have discussed so many deposition techniques in physical process. In next class, we will discuss on the chemical deposition process. Hope you all understand my lecture. If you have any doubt, just put your questions in my chat box. I will answer to everyone. Thank you for your patience. Thank you so much. We will see the another class. Okay, thank you.